Hello students. Today's topic in basic engineering mechanics is internal forces, axial force, shear force, bending moment, twisting moment diagrams. These are the basic concepts and I am Dr. Sushanta Chakraborty, Associate Professor, Department of Civil Engineering, IIT Kharagpur. You know, in any engineering structure, as for example, machine, building, bridge, airplane, etc., a large portion of the load carrying members are actually slender members. The length of a slender member is comparatively much greater than either of its cross-sectional dimensions. The use of slender members is a much more efficient load-carrying arrangement with minimum usage of material as compared to a complete 3D arrangement of supporting a load. Examples of slender members are beams, usually they are horizontal and resist moment. Their columns, usually vertical and takes compressive force. You have seen in buildings and others the columns. Shafts, usually circular cross section and transmit torque. Look at your study table. The legs of the table are slender members. They are columns basically. Slender members can also be in a loop or in the form of a coil. Not only straight, it can be bent also. While carrying a system of forces and moments, a slender member can be pulled or pushed, bent or twisted. Such effects, although can occur in combination, one of the effect is mostly predominant in a particular type of application. It is useful in engineering design to express the variation of one such effect at a time along the length of the slender member, and these variations are usually expressed graphically. You see, I have drawn casually a figure of a 3D and a slender member just to show you that the length is much larger than the dimension in the cross section, but a 3D object, all the dimensions are comparable to each other. Method of analysis, our interest in basic engineering mechanics will be to analyze such slender members and see that how we can apply the equilibrium conditions. The equilibrium requirements of a slender member as a whole, as well as of any part of it considered separately, must be well understood. The interest is to determine the resultant forces and moments acting across any cross section of the slender member due to the applied and the reactions which are generated through this application of the external loads and moments. For this, first the external reaction components, that is the forces and moments at the supports of the slender member as a whole, are determined. That we have done already in several occasions from the free body diagram and finding out the reactions. Then a hypothetical cut or section. This is new to you in this chapter. We will have a hypothetical cut or section across the member at the point of interest along the longitudinal axis of the slender member. We will consider that, and a hypothetical cross section divides the slender member into two parts. We can then consider either of the parts and we explore the forces and moment required at the cross section to keep that particular part into equilibrium with the external active force system and the external reactions from the support acting on specifically on that part. You will understand better when I express graphically. Just be with me with the descriptions. Usually the forces and moments at that cross section are resolved into components. We will talk in terms of components. It is normal component or as well as parallel to the orthogonal reference axis. So you see that what we mean to say in our basic engineering mechanics, our intention is that to analyze the slender members for equilibrium, and what we are going to do to understand the forces and moments acting over a cross section of that slender member. We will later on realize what are the use of it, but right now you get a sense of it. Suppose there is a slender member, a beam type of thing. It is supported, simply supported, two supports. There are active system, one force acting here, one couple acting here. So what I am interested, if I pass a hypothetical section, I have just indicated it here, perpendicular to its longitudinal axis and cut this into two parts, then I must understand how to keep that part into equilibrium. That means if I remove this right hand part, I have removed it here. So there will be forces and moments from the 3D equilibrium concepts. They will be acting over this cross section to keep that part of the beam into equilibrium. It has to be. If the entire structure is in equilibrium, if I pass a section to divide into two parts, then the individual parts should be in equilibrium. That cannot violate the static equilibrium. So similarly, equal and opposite forces and moments will be actually working. I have shown it as a negative phase. Here also, I have not shown all the forces and moments here, just for clarity. At least you can understand that there is a force here in this direction, which is along the longitudinal axis. There are two force components along the x, y, and z axis. There are moments around the x, y, and z axis. So our 3D equilibrium, that forces and moments along the axis forces and about the axis moments, all these 6 components, if we consider acting as a resultant on this cross section, then with these force and moment components and the active forces and the reaction from the support into that part should be able to keep this part into equilibrium. That's what we say. Similarly, equal and opposite, these forces which have generated after cutting the section, they will be applied to the phase. I say this is negative phase and we say this is positive phase. Positive phase means the x-axis in the positive direction has emerged from it. In fact, the y-axis and z-axis positive directions have emerged from this section, and this is we call positive phase, and this is negative phase. So next, our intention is that these components of forces and moments acting on the cross section have different effects on the slender member as we understand, and have been given specialized name like the axial force, which will be producing tension and compression along the longitudinal axis, shearing forces, displacing parts normal to the longitudinal axis, bending moments, bends the member about the axis perpendicular to the longitudinal axis, and twisting moments, which will twist the slender member about the longitudinal axis. I know that these descriptions are difficult for you to conceive. We will see through diagrams. You see, first let us count that what we have seen, what we have done. We have cut the beam into two parts, and over the cross section we are examining what are the forces and moments acting along and also about the axis. So this px force component will pull the beam at the moment. It could have compressed the beam also if it is in other direction. Right now I am putting all the forces and moment into the positive sense. Means if this is x-axis, this is z-axis, and this is y-axis, it's a right-handed system. So px will pull the beam, vx and vy both will shear the beam. That is, it tries to displace laterally. This is pull longitudinally. Pull longitudinally, displace laterally. Then my will try to bend it about the y-axis. It tries to bend. Similarly, mz also tries to bend. And mx, it will not try to bend, it will try to twist the beam about the longitudinal axis. So these are the effects. Please remember this diagram very well with the notations shown. If you differ from this notation, you have to be consistent. So right now, I will advise you follow me, and I am following a textbook. So this force component, 3 force component, 2 components are shearing forces. Actually, they are acting parallel to the cross section, and another is perpendicular to the cross section. This is pulling, this is shearing, this is bending, my bending, mz bending, and mx twisting. Let us go ahead and see that what are the effects. The equilibrium equations so far learned are sufficient to account for the magnitude of such forces and moments, and that is our intention. The deformations and resulting stresses will not be discussed and kept pending for the subject matter related to strength of materials or mechanics of material, and we'll learn it later. We are not considering any deformation of material. For us, it's a rigid body. To start with, we will initiate our discussion with the kind of a slender member called beam, this being most popular in application. And later on, we'll tackle the shafts for torsion and axial member for axial forces. The internal effects are predominantly shear and bending for the beams. Now, let us see the diagrams. It will further clear your mind what we mean to say. Once again, the diagram is redrawn here with the force component, axial force, shearing forces, bending moments, and torsional moments or the twisting moments. And you see, the effect of the axial force is to actually separate the member like this. And the effect of shearing force is to shear it. That means it just laterally comes down one part with respect to the other. The bending moment bends the whole member, and the twisting moment actually twist or provide a torsional actually moment. And in the beam, we will not consider the twisting moment. Also, for simplicity, it's a 2D beam, 2D effect. So the off the plane shear Vy also we will think of absent. A beam is usually not predominantly subjected to axial forces. So we will consider. And also the Mz is a moment which is about the z-axis also we can neglect, and we can say a beam in 2 dimension will be predominantly subjected to this moment my and vz. This my, which will be acting over the cross section, and the vz, which will be also acting over the cross section parallel to it, they will be able to equilibrate the beam in 2 dimensional if the loading is 2 dimensional, along with the reactive forces and moments. So in the beam, now it is a 3D picture. If you see through this towards the beam, and if I project it and draw a 2D figure, it will be the figure which I have drawn below, the left part of this figure. So this is the moment My here drawn as M, and the shear force Bz is drawn as V. So this is the 2D figure of this 3D figure. Now, I should continue with the part which I have left. I have shown you that this is another part which I have left, and I should also draw in 2D that part separated out as if, and it is actually not. Just to show you the moment pair, so there will be equal and opposite moment acting at that section, equal and opposite shear acting at that section, so that if you join the left part with the right part of the beam, the internal forces vanishes. And our point of discussion is the internal forces. For that, we must separate out the two parts and examine one pair of it. And that's how you can find out the moment and the shear required at a cross section to keep it in equilibrium. That is our point of discussion about the bending moment and the shear force diagram. Next. So beams, before we actually start the discussing about the bending moment and shear force diagrams, let us understand some basics about the beams. So we are still with the rigid bodies. Beams are long, at least 5 times of either of the lateral dimensions. It is prismatic, usually no change in cross section along the length. It is slender member, which offers resistance mainly against bending or shear. It is transversely loaded usually. That's how it is most efficiently serving. The relationship between the applied external forces and moments with the internal resistance of the beam, that is the shear forces and bending moments, over the cross sections need to be established. That is our point of discussion in this particular topic. Before exploring this, let us learn some basics about the beam, its typologies, and nature of supports. So instead of describing different kind of beams, you will see this video later. I'm going directly to the diagram and explaining what I have written here. You can later on see that's what I have written. So you can see that the types of beam according to the support conditions you are already familiar with. If the supports are just sufficient and we can find reactions from the static equilibrium equation, we call them statically determinate beams. If we have more supports than necessary, we have statically indeterminate beams. Into the statically determinate or even sometimes indeterminate, we'll call a beam simply supported if we have supported it at one end and the other end. In one end, you have seen that this is called pinned support and this is called roller support. In the pin, actually the rotation is allowed but not any other movement. In the roller, the rotation is allowed along with a horizontal movement of the beam. This is called simply support. A cantilever beam is rather it is fixed at one end, completely embedded in a wall, and it is free at other end. Your veranda is a cantilever slab basically. There are combinations of the simply support and cantilever, and this portion is usually called overhang to the simply support, this combination. Sometimes the beams are continuous, that is, you don't need, but there is an extra support to share the load. That's good, but there are other issues you will learn later, that there are secondary moments and secondary effects which will be there due to the temperature change or lack of it, that we will learn later. Now, end-supported cantilever, the cantilever here is supported at the end, which it does not need for its equilibrium. So you have an extra support. We will see that this is not possible for us to solve it from the static equilibrium condition. Now, there are fixed beam also, both side fixed. Nice, they have very less deformations, but usually the moments will be developed at the ends, which you cannot avoid. So these are the typologies of beam according to the support conditions. There are types of beams according to the loading, and I've drawn some diagram very casually actually. So this is a beam representation of the beam by a line. We will make like this henceforth. This is a concentrated force. A force does not occupy much space for its connection to the beam, and this is called concentrated force. You can imagine that stresses will be very large, but we are discussing rigid bodies. So for us right now, it doesn't matter. It rather helps us to understand that where the load is located with respect to the support. There are concentrated couple or moment also may be applied to the beam. So, and also there are uniformly distributed loads onto the beam. Suppose you are standing on the beam, this is concentrated force. You are lying down on the beam, it will be uniformly distributed. Sometimes the distribution is not uniform but varying. Sometimes we have a triangularly varying load which gradually increases. And sometimes we have a general distribution. We know the nature of this curve of distribution and we can find out the total load or its center of gravity, or we can deal with, no problem. Now, if thus I have extracted this diagram from Merriam and Craig, it is so nicely drawn that I have not tampered with. I'm directly quoting from that if you have a uniformly distributed load, for finding out the overall reaction, you can afford to have this load reduced to its equivalence. Suppose if omega is a distributed load, suppose once again, you are standing here, suppose your weight is 60 kg. You are standing, so concentrated force is 60 kg. Suppose the beam is of 2 meters. So now you lie down, suppose you occupy the full 2 meters. You are 2 meters long and your weight is 60 kg. So the uniformly distributed load will be 60 kg divided, 60 kg is the mass, sorry, I should have converted into 60 into 9.81, that you do, but just for explanation I'm telling, 60 kg mass, equivalent weight 60 into 9.81, that your Newton, and then divided by 1000 kilonewton, and then you can have divided by 2 meters, half of that will be the uniformly distributed load kilonewton per meter. So you can reduce that load to equivalent load by multiplied by the length, and you can also find the CG very accurately and easily at the midpoint. If it is triangular, you know 1/3 from the right side or 2/3 from the left side is the center of gravity of that load. And the area of the triangular load diagram will give you the total load, half omega L. Similarly, if you have a combination, a trapezium, a trapezoidal loading, you can divide into uniformly distributed and a triangle and deal similarly. I will advise never join and these two loads to find out its CG, and don't spend time because you can deal with different separately. And also, if you have a general load distribution, you can integrate it and get the total load and also find out the center of gravity of the loading to find out the moments, etc., the bending moments and the shear forces. So now come to our actual business, the theory part, the internal effects, shear and bending over a cross section. I'm spending so much of time with you for initial making you understand what we are actually after. So we are making a cross section of the member, and we know that due to the external load and the reactions, there will be a moment and a shear which will be equilibrating that external load and the reactions, and the part of the beam will be in equilibrium. Similarly, we can deal with the right part or left part, and if this difference is very less, in fact, if it merges, we will define the moment and the shear at that section. For this is what we follow, and this is a sign convention we will follow. Please remember, if you consider the right part of the section of the beam, the right, left up, right down. So if you are on the right part, then right down shear we will take as positive, and anti-clockwise moment we will take as positive moment. This is positive shear, this is positive moment for us if we consider the right of the section we are having. And if we consider the left part, it is left up shear which is positive, and a clockwise moment will be positive. This sign convention is arbitrary. You can change it, but I will advise stick to this for time being. It is mainly followed by our textbooks, and you will be benefited right now immediately that it is easy to draw the shear force and bending moment diagram. But once you stick to a sign convention, it cannot be changed within the problem. The next problem you can change, but who wants to change for each problem a sign convention? Once you are set with a sign convention, it will be you will have a intuition in mind about the sign convention and follow that. There is no harm if you follow the other sign convention and you interpret it correctly. Now, the general procedure for then drawing the shear force and the bending moment diagrams, we will understand it through examples. So don't worry if you do not understand the general procedure. We will better understand through examples, but I have to state it formally that we will determine the support reactions from equilibrium of the beam as a whole, select a location along the longitudinal axis of the beam, pass an arbitrary transverse section through that point on the longitudinal axis, isolate the portion of the beam either to the left or to the right of that arbitrary transverse section, and determine the shear force B and bending moment M necessary at that cross section to maintain equilibrium of that part of the beam. Once you do that, then shift this arbitrarily located cross section to different locations as you like. But it's not very large locations, because you will understand the salient features of the beam and you will find only a few locations. If you determine the rest of the thing, you can join either linearly or non-linearly if you know the distribution, and draw the variation, that is the diagram, the shear force diagram and the bending moment diagram. Join the discrete values of the shear forces to complete the shear force diagram, and join the discrete values of bending moments to complete the bending moment diagram. That's what we are going to learn now through examples.